The high-voltage system for microwave ovens utilizes a voltage doubling circuit to convert 120 volts alternating current to a negative DC pulse of 4,000 volts to produce microwaves in a magnetron tube. Alternating current can be thought of as a series of sine waves that alternate from a positive charge to a negative charge. One change from positive to negative is one cycle. In most homes, one cycle of alternating current is generated at a rate of 60 times per second. The number of cycles per second is known as frequency. The high-voltage circuit in a microwave oven operates on using the positive and negative portion of each sine wave. The high-voltage circuit depends on using two fundamental characteristics of electricity. The first is that the electricity always follows the path of least resistance. The second is that electricity in a closed circuit will always flow from the hot side of its source, or the more positive side, to the less positive side or neutral side of the source. The first component of the high-voltage circuit is the transformer. The transformer has a primary side through which 120 volts of alternating current is sent. This device does two things. One secondary winding steps the voltage down to 3.8 volts. During the positive portion of the sine wave, because we have a complete circuit, current will flow from the hot side of its source or power supply through the filament of the magnetron to the neutral side of the source. During the negative portion of the sine wave, current will flow in the opposite direction. The 3.8 volts causes the negatively charged electrons on the cathode of the magnetron to become excited. In this excited state, these electrons are available to move freely within the vacuum of the magnetron tube. If no further voltage is applied, the electrons will remain free-floating since the filament switches between the positive and negative charges of the alternating current. The other secondary winding steps the voltage up to 2,000 volts of alternating current. But even this much voltage cannot overcome the natural resistance within the magnetron. Twice that amount of power is necessary. The nearly 4,000 volts necessary to activate the magnetron is developed through the use of a voltage doubler circuit containing a diode and a capacitor. Both the positive and negative portions of the sine wave are used in the transformer's secondary winding to provide a total of negative 4,000 volts of direct current to activate the magnetron. During the positive side of the sine wave, 2,000 volts will flow from the hot side of the secondary winding. From the hot side of this power source, current will flow through the circuit to the neutral side of the source. The diode in this circuit does not provide any resistance when the electrons flow in this direction. The capacitor will receive and hold the 2,000 volts generated by the transformer until it is provided with a path through which it can discharge the stored energy. The electrons cannot flow to the neutral side of the power source through the diode because the diode blocks the flow of electrons backward through it. There is not enough energy to overcome the magnetron's naturally high resistance. The electrons must remain stored in the capacitor until additional energy is generated. During the negative sweep of the alternating current, electrons will flow directly from the secondary winding's hot side, seeking the neutral side of the power source again, as long as a complete circuit is available. The high voltage has only one path to follow to get to the neutral side of the power source. With the applied energy from the transformer of 2,000 volts, plus the stored energy of 2,000 volts from the fully charged capacitor, there is enough power to override the high resistance of the magnetron. The 4,000 volts fires through the magnetron on the negative portion of the sine wave, thus creating the negative DC pulse of 4,000 volts. The energy that is stored in the capacitor during the positive sweep of the sine wave is added to the 2,000 volts that is generated during the negative portion of the sine wave and produces 4,000 volts to fire the magnetron. This is how the negative DC pulse of 4,000 volts is produced. This voltage must pass through the magnetron's cathode, forcing the freed electrons to rush toward the anode of the magnetron. A permanent magnet is placed around the anode of the magnetron to force the electrons into groups that take on the appearance of the spokes in a rolling wagon wheel. As these groups of electrons hit the vanes on the inside of the anode, it begins to vibrate. A small transmission antenna tuned to 2450 megahertz is attached to the anode and also vibrates. These then are the microwaves that cook the food.